Thank you so much, Laurent, and also Marie for having me over. This is my first time in Marseille. Very interesting. So before we begin, I understand this is a fairly mixed audience. And I was actually quite impressed all throughout this week, talking to many of you, that some of you actually are, very entrepreneurial and very intrepid in being, I guess, one of the few people in your group who are actually studying quantum. Okay, so in that kind of interdisciplinary spirit, this is kind of the angle that I'm starting with this talk. I mean, a lot of you guys, you do PDEs. And some of you now have been introduced to what quantum simulation is. And it's very much an interdisciplinary topic. Okay. One, you've heard all throughout this week from a more computer science and more mathematical viewpoint, okay, what quantum simulation is. But actually, I would say that the topic is very much buried in physics. All right, so if you think about what quantum mechanics is, well, actually, when it's first introduced, it's introduced as a PDE, right? And the PDE of that is actually Schrodinger's equation, which many of you would have seen. And now our question is if how quantum simulation got started with Feynman is the more famous one for studying, but actually was proposed earlier on as well, which is using a quantum device to actually simulate a particular type of PDE. Only, and that is Schrodinger's equation. Now, and it was proposed for resolving what is known as the curse of dimensionality, and this is what you guys have heard, throughout this week. And now our question is, well, what about other kinds of interesting PDEs? Okay, can they also be simulated on a quantum device? And the natural first question is, well, how do we, in order for it to be simulated on a quantum device, and thereby also maybe resolve a curse of dimensionality? It should then be mapped onto something that may look like a Schrodinger's equation. Okay, and this is what we're going to explore for the next 3 sessions, I guess. And it's a method that we call schrodingerisation, and I think it's a very self-explanatory name, right? How do you turn non-Schrodinger's equations into Schrodinger-like equations so we're able to simulate this on a quantum device? Now, a lot of the methods, again, that you have heard all throughout this week, they belong to what are called discrete or digital type of methods. And again, this is very familiar to you guys who work in numerical methods and so on. And I'll speak about this a little bit more. And you rely on these discrete type of methods because the classical computers that we have today, they've actually already evolved after a fairly relatively long history into digital devices. But actually, the beginning of computing, they started off with analog devices. Okay, they use real physical systems, okay, which are continuous in nature, okay, to simulate ODs and PDs. Okay, so we're going to go from both angles, but primarily, I think, just to make it different, okay, from what you guys have been introduced to, and what's been talked about mostly, from a continuous viewpoint. Right, to learn these techniques, and then we can discretize these a bit later. Okay. But before we begin, can I have a show of hands, for those of you who maybe you're the first in your group, or among the first in your group to actually do quantum computing, and this is kind of your first quantum computing lecture, lecture series sort of thing. Okay, great. So that's almost a third of the room. All right, so I try and cater as much as possible. And because this is still a fairly intimate group, we will have topics where we can choose to go more into them if more of you would like to, because again I know many of you are staying, right, for 6 weeks. And if there are other topics you don't want to hear about, then we can skip over them, maybe go into others in more depth. So this is kind of very flexible. And also I would welcome any questions in between as well. Right, so at any point, if things are unclear, we're just very flexible, just to make sure that we're on the same page. Okay, good. So this is part 1. There will be kind of 3 parts to this. But before we begin, just some general philosophy, I guess about how we are approaching quantum algorithms. Well, first of all, why quantum? Okay, and I guess we sort of take it for granted. The old story about Moore's law, the size of chips. And I guess there was a lot of quantum crypto talks. Okay, as well. In terms of security. But there could also be there are also classical bottlenecks in things like energy, memory, communication, right, as well as time kind of costs. And what we're going to look at. Just in the next 3 lectures is primarily not on the above, but just in terms of time cost when it comes to simulating our algorithms. But it could be that we can extend some of these methods to also look at these other areas as well, including quantum memory. But the key message that I want to give, what makes learning about quantum algorithms and actually devising new quantum algorithms, which really I think should be at the forefront of everybody here, who's doing research, how is it different from approaching classical algorithms? And I think one of the main things is that to think about how, because the underlying physical infrastructure has changed, we have to fundamentally change the way that we think about algorithms, actually. Right, so I'm just for a bit of background. I'm actually a physicist. I was a math major, but I'm a physicist. So when I think about computation, I think about it as a physical process because every single piece of computation you can think about, it's actually embedded, right? Not just in physical matter, but in the physical law, right? That takes you from one physical state to another physical state. And there are many different ways of thinking about how to embed the data. And many different ways in thinking about how to actually perform the evolution, because you can perform the evolution in a discrete way, or you can perform the evolution in a continuous way, which is how nature does it. Okay, so therefore, not just the computational techniques, but actually even the mathematical language, as we'll see later, that should really change when the physical infrastructure changes. All right, and I'll introduce maybe 2 main ways of thinking about this, and 2 main, I guess, mathematical languages that we will use. But in terms of the philosophy on how we approach this, not just from more of a physics angle, because since we're at the beginning of quantum computing, we actually don't know the best infrastructure, right? And we still, at the beginning stages, we think about historically classical computing. Most of you are too young to remember this, but classical computers actually started off with analog devices, right? And I've spoken to some of you who actually work with wind tunnels as well. Okay, that's another analog simulator, which are specialized type of devices. So we're still at this stage where we can actually explore some of these maybe old style, type of computation, which is much more intimately embedded with the actual physics, what's happening, And once that's been very well established, and once we have fault tolerance and so on, this is what we heard at the beginning of the week, then we can, rely on more of the classical, numerical techniques and that kind of thing. But at this moment, I think we're very lucky because we can explore all these different areas, because the technology itself is not mature enough that we can take advantage of the different underlying physics, that's happening. And the philosophy should, I think, not only that, devising algorithms where we can show that it is possible to perform something with a particular, you would have heard about, query complexities and all these complexities in a very computer science kind of language, but it should also be as simple as possible. And now, how to define simple is something that is, well, I guess that's very difficult. It's not, we don't quantify, we don't have a complexity measure for what we mean by simple. But here, I think all of us, we have an intuitive sense, right, when, an algorithm, you don't need to maybe think, as much, right? You don't need to make as many manipulations, and it should be as easy to program as possible, once you learn about them. And that's also the angle that we have. The algorithm should be as simple as possible, but no simpler, of course, So hopefully this prepares our mind to what we're going to think about over the next 3 lectures. So you guys know what quantum simulation is, but typically, so you start off with a quantum state, and you want to ask the question, what is the form of this quantum state after a particular time? So you've been introduced a lot to, if you have, a system or, say, n 2-level systems, or n qubits, what's going to happen. And even, memory, we know the classical vector, even to input the information, of this state, that's 2 to the power of n entries, So this is the, normal argument. And of course, if you want to then simulate what happens, we know that, quantum evolution is a unitary operation, it's reversible. And it's typically thought about in this context as a large matrix, And if you want to do matrix multiplication, again, that's also, order, more than order n, 2 to the n. However, actually physical materials, or physical matter, it's not just in terms of two-level systems, as we know. And actually, I think in the first lecture, you even saw that there is no such thing, really, as a fundamentally two-level system, right? All physical systems, as far as we know, unless we go to the quantum gravity limit, okay, all physical systems are continuous. They operate continuously in time and space. And only when we take certain limits, if we add in damping and so on, then we can approximate, okay, the information using zeros and ones, right? But actually, they're naturally continuous, right? So, and actually, in quantum simulations, you can also perform them with, the fundamental quantum systems, and they're actually called continuous variable quantum systems. So, quantum computers with qubits, order hundreds right now. But with these continuous variable modes, we call them Q modes or quantum modes, people can do millions now, okay? And the question is, can we exploit these to do simulation? And in particular, ones of interest to us, right? And because we're concentrating on PDs, if you think about where PDs come from, okay, mostly they come from physical systems, which are again continuous. So do we really need to discretize, okay, everything, right, and then put them onto another discrete system that we've discretized? At least in the formulation, okay? So, so again, we have these two types, okay, of quantum system to think about. All right, so we claim, okay, we want to use quantum simulation for differential equations and partial differential equations. But where do these differential equations come from? Well, the ones of most interest to us, right, us collectively. Well, if you go to the top of the scale, so we have space and time, okay, so the very large scale things, if people care about fluid dynamics, okay, very large scale systems. And if we go down a little bit, okay, we have kinetic theory, okay, in smaller scales, maybe molecular dynamics and people interested in quantum chemistry, and towards, the quantum mechanics. And you say, well, okay, well, if the point is, all physical systems, as far as we know, right, they originate from quantum mechanics, then of course, we already have quantum simulators, right? Like every one of us, we're already quantum simulations, right, of the dynamics that, we're obeying right now. So certainly we know, because you guys are mathematicians, you want existence proofs. That's your existence proof right there, okay? It is always possible, right, to map, right, fundamental quantum mechanics onto, to map other physical system onto quantum mechanics. But of course, as mathematicians, that actually to go across the boundaries of these is a very, very, very difficult series of mathematical problems, right? People win Fields medals just to, look at one aspect of how to cross between one boundary to another, right? But certainly nature somehow does it, so it is possible. So you're like, well, okay, so is that it? Okay, we say this is how we do quantum simulation. Well, no. Because the point of us going through all this trouble doing quantum simulation, because we do want to resolve the curse of dimensionality. So if we think about the fundamental quantum mechanics, okay, that simulates us, okay, right now, like how many particles do we have? Like I think it's like 10 to the power 17 or something like that. Okay, and well, so that will be a very, very high dimensional quantum mechanical problem, and that will not really help us resolve the curse of dimensionality. Okay, so the trick is, right, to find that if it's possible to map the classical equations, which is on the larger time and spatial scale, onto the a fundamental quantum mechanical equation, a Schrodinger-like equation, without increasing the dimension too much. Okay, and the particular Schrodinger method that I'll tell you about, it's increasing dimension by 1 if we're looking at linear partial differential equations. Okay, so and this in itself, it's interesting that there should exist an exact transformation. Okay, in that way, and we can come back to that maybe in the discussion session for what fundamental ramifications that has. But I'll just tell you about the more maybe practical aspects during these lectures. Okay, so ODs and PDs. Okay, you guys know what it is. Okay, so now the question is, how do you put that onto quantum hardware? And the question is really about mapping, right, equations of the form. Okay, either a system of d-dimensional ODs or d+1 dimensional PDs into Schrödinger's equations, and in italics in a simple way. Okay, so you would have heard about in the previous lectures, or Agnieszka talked a lot about block encoding and these type of methods. Now it's always possible to make something non-unitary unitary, but for the purpose of simulating partial differential equations, is it actually the simplest way of doing it, right? In a way that is as natural as possible. Okay, so we'll talk about, in italics, simple way, okay, and we'll talk about Schrödingerisation. I'll just briefly go over, what we're going to talk about in the next 3 lectures, and maybe, and having this handy so you guys can tell me what, you want to hear about more and what you want to hear about less. Okay, so, all right, so like part 1, so this is today, and we'll probably run into tomorrow as well, which is just the basics, okay, of schrodingerisation. And we're going to look at just linear partial differential equations, because there's really already a lot to say about linear, okay, PDEs. And I'll talk about 2 types of formulations. Okay, so you guys are now more familiar with the previous lectures about the digital setting, okay, like Lee Trotter, and so on, block encoding. And LCU, type of methods. Okay, they're usually in the discrete phase formulation, and by that I mean, qubit-based type formulations. And time doesn't run continuously. But actually, I would like to begin with talking about things in the continuous time and space formulation. Okay, formulate things exactly. Because again, the Schrödingerization formalism that we have, we can use it for the discrete setting, but I'd like to introduce everybody through the continuous formalism. Like firstly, I think to help us think in a more physics way, okay, because I feel like that actually encourages us to think about new algorithms. But secondly, I think it is more natural in the sense that the PDs that we're trying to simulate, they're continuous to begin with, okay? So, and because the mapping is exact, right, and that allows us to do this. We're going to look at homogeneous ones first, and then inhomogeneous, high order time derivatives. And we also talk a little bit about ill-posed linear PDEs, so that might be of interest, for inverse problems, things like that. Boundary conditions, and the last part, just if you guys care more about improving, okay, the complexity, okay, of these, so we can, further ameliorate, enhance the algorithm. It would reduce the simplicity of the algorithm, but it is possible to do, okay, to enhance the precision. Now the part 2, okay, so that's probably tomorrow, and maybe it leaks into the 3rd part as well for Saturday. So these are the special topics, and you guys can tell me what you want to hear more about or less about, okay? But we do have topics prepared. So nonlinear ODs and PDs. I know some of you, are interested in nonlinear, but I won't talk about general nonlinear ODs or PDs because this is still very much an open problem. Okay, I only talk about some nonlinear ones. Uncertain ODs and PDs. Anyone work on uncertainty quantification here? Okay, cool. So we have a session on uncertain ODs and PDs. Non-autonomous ODs and PDs. Anyone interested in non-autonomous systems? Nobody? Okay. Oh, maybe. Okay. All right. Yeah. And then the last part. So Agnieszka's not here, but she talks a lot about linear algebra problems. So, and we can also, look at linear algebra type of problems. Okay. So related also to ground state and thermal state preparation from a continuous viewpoint. Okay. So we have that as well. And the 3rd part, so again, I think this probably leak into the Saturday session. So if any of the topics you guys want, more in depth in part 2, we can leave for Saturday as well. We can go through some examples and explicit circuits. And is Shajir here? Okay, so Shajir with a hand up. So he's my PhD student, and he works a lot on explicit circuits. And this is the idea that once we do have fault-tolerant quantum devices, and we do have these dual devices, it's actually not enough, to just simply have Curie complexities, okay, for different algorithms and having asymptotic results. We actually want to see the real circuits, so we can actually program them into real quantum devices, okay? So he's doing a lot of that work, and he's also an intern now in one of our quantum companies. It's called Unitary Lab. So we're going to debut our software here with you guys here in CEMRACS. So it's a software that we have for what's a classical simulation, like for PDEs, but he has embedded in there, okay, a lot of the quantum techniques. So if you want to play around, if you have projects later, okay, this is something we can use. And then, only if we have time, there are some extra topics as well, but we might not have time for that. Okay, all right. Okay. So again, I want to go back to the language a little bit, okay, about. Because usually when people think about ODs or PDs, they kind of launch straight into numerical methods, okay? But I think that's probably not the right approach for our particular era, okay, in computing history. right? Because maybe after the 60s, when we realized we can use these digital devices, and people don't really think about the infrastructure anymore, and then they go straight into different ways of discretizing, okay? Maybe different stability properties of one versus the other, and all these things for different PDs, and you don't think about anything else. But I think we're at a different era in computing history because we don't have the quantum devices yet. We don't know the final infrastructure, and we're not even sure, when we're going to get fault-tolerant quantum devices. So is there something we can do before that comes along? Because there was a period in computing history that classical bits, were not easy to deal with. This is why people needed classical, error correction, which is, and we heard talks about that. And actually, computing began with analog devices. And anyone's heard of analog, like the term analog devices? Okay, a few of you. Okay, quite a few of you, yeah. So, so this is actually a great opportunity for us to explore, okay, these different types of infrastructure that allows us to use these different mathematical languages, okay, as well. So if we look at, PDs, like, we can look at it in the purely continuous way, both in continuous time and continuous space. Okay, well, ODEs are naturally continuous in time, but discrete in space. And linear algebra is discrete in both. Okay, so typically, we change PDs and ODEs just into the last part, okay, where everything is discrete. But we can ask the question, well, what happens if we use the native, continuous nature, either, space and time, for the ODEs and PDs themselves? All right, first. So, and I'll say, to begin with, to think about this, I think we should think about there are 4 classes, right, of ways of using quantum hardware as simulators. Okay, so not everything is just qubits and applying different gates. Okay, there are actually 4 different ways, and this is dependent on the way we think about whether we're not going to discretize time or space or both. And these 4 types of simulators, okay, they're categorized by the way that we encode the spatial data and the temporal data. Okay. And whether or not they're continuous, okay, or analog, that's another word, or discrete, okay, or digital, okay, and I use these terms interchangeably. So now typically, right, when we talk about both classical and quantum algorithms, typically we're actually on the right-hand side where we think about digital case, okay, so we have, discrete space as well as discrete time. And if we're dealing with, digital quantum simulation, we're usually dealing with, either a matrix language or operator language, depending on the type of data, okay, that we have. But we can also have discrete, okay, in space, and discrete. Oh, sorry, we can have continuous in space, but discrete in time. And this is, continuous time and analog quantum simulation. So typically, when you think about like D-wave type of, algorithms, okay, so this is of this type, where you're working with qubits, but they're actually, been simulated in continuous time. And again, the language could be matrix or operator language, depending on the way you encode, okay, your data. You can have continuous space, but wait, sorry, I'm getting mixed up myself now. Okay, so continuous space, but discrete time. And often this is called continuous variable quantum computation. So some of you may have heard about that. And this is where, the actual, matter that we use is not qubits, it's these Q modes, but it's actually very difficult to simulate them in continuous time. Okay, well, in cases where, it is difficult to simulate them in continuous time, because if people would like to have universal quantum devices using these, then they also want to have these fundamental gates, but using these Q modes, okay? So this, and again here the language is infinite dimensional vectors, okay? That's acted on by operators, okay? Or we can just work with, qubits, or anyone's heard of QDIDs? Is this, okay. So it's basically just, qubits, but, high dimensions, okay? And the language there would be, like usually with matrices or vectors, finite dimensional vectors. And just as, I guess, some word of intro, okay, because we do want to talk about, continuous variables later, but just as a reminder, okay, that, whenever we're dealing with digital quantum information, the mathematical language that we use is the matrix language, okay, which we've seen all week, okay, so, with vectors in Hilbert space, and then they're acted on by, finite dimensional matrices, okay. And typically, okay, if it's digital also in space, then a lot of the algorithms that, and again, these should be quite familiar. Okay, so you're breaking up a large matrix and you put them into little chunks, which kind of doable chunks. And I kind of think about them as Lego blocks, right? So you have a finite number, possible Lego blocks, and you can build whatever you want. Okay. But you can also have continuous space. So this is now the Q-mode language, or continuous variable language. And this is something people typically don't talk about so much in quantum computation. And in fact, so there are many people who haven't even heard about the term Q-mode. But I would actually argue this is the fundamental unit to consider, because this language is basically a wave function. Right? And this is beginning of quantum mechanics. Actually, qubits is something that's a bit weird if you're a physicist and you learn about quantum mechanics. The fundamental piece of information actually is that of a wave function. So now if we think, now the space that we live in, instead of a finite dimensional Hilbert space, we're living now in infinite dimensional Hilbert space. And the basis vectors, right, instead of 0, 1, or for qubits, 0 to some dimension d. Now this is infinite dimensional, and one way of thinking about possible bases are things like the position of momentum eigenstate. Okay, so here now, if we're in finite dimensional space, then we have the summation sign. Okay, but an integral is just a summation. Okay, except now we're summing over infinite numbers. So now we have the summation goes to an integral sign. But now now instead of using finite dimensional matrices that operate on these states, now we promote these to operators, so essentially infinite dimensional matrices. And I would introduce two primary ones that we're going to use throughout, okay? And this is where quantum mechanics began, actually, with these operators. So quantum mechanics began when they looked at what classical energy form looks like. You have your kinetic energy part, right? And you have your you have your potential energy part. And then they said, well, okay, what happens when we promote things like x and p, okay, position and momentum, to become operators? Okay, and Heisenberg, you guys know about the uncertainty principle, okay? The fact that, quantum mechanically, our position and momentum operator, they actually don't commute with each other, okay? So our x hat and p hat. So now our basis set, okay, can be x, the x ket, so these are the position eigenstates, and the x without the hat, that's the corresponding eigenvalue. And we have the p hat, okay, the momentum operator, and we have the corresponding eigenvalue of p, okay, and these form a complete basis themselves, okay. And the fundamental observation is that these operators don't commute, okay, and these are the fundamental operations to use when we're dealing with continuous variable quantum states. And something else that is really interesting, okay, when we think about position momentum eigenstates. Okay, so one really important observation is that if we take the inner product between them, okay, they become e to the power of minus IXP. Now, where have we seen e to the power of minus IXP as mathematicians? Right, we need to take Fourier transforms. Yeah, okay, so you've heard all week, a lot of the power in quantum algorithms really comes from doing the quantum Fourier transform step. Okay, and here we see that actually in the continuous formalism, somehow this factor comes in naturally. So in continuous variables, actually a quantum Fourier transform is really simply changing something like your position eigenstate into a momentum eigenstate, okay, and vice versa. And we'll actually see that this is actually quite easy to do. So unlike the qubit-based formalism, on optical systems, for example, it's very simple, okay, to change between x and p. Right? It's really just changing a basis in which you make your measurements. Okay? And if you want more details on how people do this in quantum optics, you can come and ask me. But this is actually something very natural, okay, to do. All right. So, and I think this is a very important kind of observation that that to do Fourier transform or inverse Fourier transforms, we can naturally exploit, or we can exploit the natural degrees of freedom. Okay, these x and p's that we have in quantum systems. And another correspondence we're going to use a lot, okay, throughout, because we're dealing with ODs and PDs, are things like derivatives, okay? So it turns out, well, I think the first correspondence is quite easy to see, right? So if we have say in our OD or PD, we have part of a function, which is x multiplied by u of x. And we want to represent this in terms of a quantum state. Okay, what can we do? So if we imagine the u-ket, okay, up there, it's really written as an infinite superposition, right, of like in terms of our x eigenbases, but the amplitudes corresponding to them is u of x. Okay, and this is a function that we care about. Now, if we act upon x hat, right, on, okay, I can use my laser pointer now. So now if we perform x hat on the left, right, we carry this over, and this is the same thing as performing x hat. Oh, sorry, my laser is not. Okay, so we perform x hat in front of this ket. Okay, but we know what happens when we perform x hat on the eigenstate x, because it just becomes, right, the eigenvalue x times this. Okay, right. So which means that if we perform x hat on u, then essentially it's saying that we have this integral now, but we can actually have an extra x now at the front. So now the amplitudes, right, corresponds to x times u of x. Right. So now if we think about this in a, if we want to embed the information of x u of x in a quantum, in the amplitudes of a quantum state, that's the same thing as applying the operator x hat, right, onto the state u. Yeah? Are we cool? Yeah? So the next part, right, say, well, what happens when we have the derivative of u of x, okay, with respect to x, right? Can we now replace that, right, in terms of how we, act onto a quantum state? And in fact, we can, right? So if you take I and p hat, right, and you perform, okay, I p hat on the left, right, and we know that, we have, that that's the same thing as applying, p hat onto x, right, but we know that because x and p, they independently form your orthogonal basis, so all we need, right, is to replace, so we have p of hat, x, then we can input another factor of identity, okay, which is the integral of pp, okay, and then if we perform p hat onto the eigenstate of p, then we get an extra p out here, okay, and then we're going to end up with this bra here with the p onto x, and here this is our inner product, and already you can see there's a Fourier transform thing happening there already, okay. And if you go through this exercise, then you can see that now you can replace IP hat with the derivative. And the physical interpretation you can also see as, because to do a derivative, it's really saying you're translating, okay, u of x. And this is what momentum does. Okay, momentum is about movement. Okay, you're changing like m times v. Okay, so mass times speed, and speed is about rate of change. Okay, of displacement. Okay, so if you're a physicist, I guess you can think about it, right? So it should make sense that the derivative u, okay, it's related somehow to momentum in this way. So later, actually all throughout, if we're in the continuous framework way of thinking, whenever we see, x, okay, u of x, we can promote the x into an operator, x hat. And whenever we see derivatives, right, like this, we can promote this to an operator, okay, which is in terms of momentum operations. Okay. And I guess we also have an exercise session for those of you who actually want to go through the exercise or the derivation. It's actually quite simple to show. Okay, this correspondence. Yeah. Do we have any questions about this? No? Okay. And remember, this is, I would like this also to be a big discussion session as well, because I guess we're pretty casual. Yeah. So if you want to hear about anything more, okay, want me to explain something, please do. Yeah, so, and we also have the Born's rule, okay, as well, okay, so this is, probability be conserved, but instead of, either, being 0 or 1, you can be, in any position, okay, x, and that's why now this is the integral, okay, this is equal to 1, and we can have, n quantum modes, and here we can express it kind of in this way, okay, where each of these, this is like a tensor product, okay, of x eigenstate in the first mode, and this is x eigenstate in the nth mode. And a very natural continuous variable quantum mode is indeed what I'm holding here, which is a laser pointer. And actually, the state that comes out here is what's called a coherent state. Okay, And we're going to use this state, okay, later as well. But you see, it's really everywhere, okay? And in fact, we are all continuous variable quantum states, okay? If we're, all right, so I've spoken about continuous space, okay, using continuous variables and using, now, this operator language. But we can also have, continuous time evolution. And continuous time evolution can be continuous in terms of if you had qubit-based systems and they evolve continuously in time, or you can have continuous variable systems that also evolve in time. And here, if we have a time-independent Hamiltonian, it's basically this evolution where you allow T now to be continuous without breaking it up into lots of different gates. Okay, and now there are many physical systems where people do have a lot more quantum control. Okay, over and actually the whole subject of quantum control, right, is actually, if you want to prepare, certain states, you want to find out the appropriate Hamiltonian, okay, that actually takes you there. Okay, so it may not need to be universal, and this is what we'll see. Like, if we care about particular problems, like particular PDEs, for example, then we may not need to care about universal quantum devices, okay, and special devices are enough, so long as we're able to engineer, okay, the right Hamiltonians. So, and I'll just, contrast this a little bit with these two types of simulation. So a lot of, what you'll hear about is digital quantum simulation. So this is, and this generally requires, fault tolerance, okay? Because, it really involves a lot of gates, okay? And of course, if you have a lot of gates and if one gate has a little bit of error, even if it's very tiny, you can see that, it will quickly propagate until you have a very large error. So this is why the topic of error correction and fault tolerance is hugely important. To deal with this. But this is, something that we'll have, further on. But something that we already have today, right, a lot of it, is analog quantum simulation. And actually, this is something that, when you go to experimental labs and you talk to people, most people now who are doing quantum, they somehow really want to get into quantum computation, but then they're like, oh, we're not, Google, IBM, or Alice and Bob, right? So we don't have these big systems, but we still want to get involved somehow. But we can't. We can only do kind of toy versions of what everyone else is doing. And then I say, actually, no, right? Because actually, when the natural quantum systems that people have, some of them, they're more specialized than others, and they're already quite sophisticated. And we'll see actually already what we have is actually enough to simulate some PDEs without these large, fault-tolerant quantum devices. Okay, by taking advantage of physics itself. Okay, so and here, so we're going to focus more on thinking about nearer term. Like, the formulation that we have, it works for nearer term as well as far term, but I will concentrate more on the near term kind of language, right? Because I think it's a bit more natural, at least to start learning, okay, about these things. Okay, so I really love this diagram because it shows you all the different kinds of quantum paradigms, okay, of computation that we can think about. A lot of the different paradigms that people usually talk about, like circuit model or measurement-based quantum computing, it's really just in the top left-hand corner, right, where you encode your data in a discrete way, meaning encoding into qubits, and also the way you process the data, okay, meaning the time is discrete, okay, so you have lots of gates, okay, so this is in the top half. But you also have, what I said, continuous variable quantum computing, and typically you work with Q modes, okay, so like these laser, the state that comes directly out of these lasers, okay, but then the processing is still discrete, okay, because if you want universal devices, you still have these fundamental Lego blocks, but now for continuous variable systems, and you still need to apply a lot of those. Okay, so this is continuous variable quantum computing. And on the bottom left-hand corner, this is where you work with qubits, but it's continuous time. And this is, a lot about, what people do in adiabatic quantum computing. Okay, so, a lot of D-wave people, also quantum walks and quantum annealing. But I'm going to concentrate more on the bottom right-hand corner. And this is kind of quantum analog computing proper. Okay, so meaning analog in both senses. Okay, so you work with continuous variable modes, but also continuous in time. And this is what I argue is the most natural, because this is how systems actually evolve. There are natural PDEs, right? And natural PDEs in nature, they're continuous, okay, in time and in space. Okay, so we're going to look at how to map problems that are continuous in time and space onto quantum analog, okay, devices. But the good thing about a continuous formalism is that you can choose to discretize whatever you want. And in fact, this is how numerical methods came about. Right? Numerical methods came about because you started off with a continuous system which you're able to discretize in different ways. And even in machine learning, because I think some of you, guys do machine learning, like ResNets, for example, right? Like we know that kind of the discrete versions, right, of Euler discretizations of ODEs, yeah? Right, so the good thing about continuous formalism is that once we have the big picture of how to deal with these things, you can choose to discretize and get different algorithms later on, okay? And you guys can choose to do that. All right. So before we go on to the actual algorithm, I just want to also mention because a little bit something about Q-modes, right? Because again, this is not a very popular way of thinking about things in quantum algorithms, because many people, in quantum algorithms, a lot of them came from computer science, but they came from computer science, post-Turing, all right? And a lot of them are much younger, so they don't remember the time of analog devices, right? So here we're really thinking about, quantum, right, Q-modes, and think about how powerful they can be. So as an example, so if we have, you guys, know all about Shor's algorithm, okay, now, right? And here we know, okay, so, and I think these numbers are actually probably a bit improved, okay, now. But for noisy systems, okay, you definitely need fault tolerance, and for noisy systems, you need, a lot of, pure, okay, qubits, and some time. But actually, when we saw what a Q-mode actually is, it's an infinite dimensional quantum system, right? So you're like, actually, well, I mean, nothing in nature is either infinite, okay, or zero, okay? But if we really have an infinite number, I mean, doesn't that mean it can contain the information of many, 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 many qubits? Okay, so even if we don't, allow, the boundaries, okay, of the universe to actually be infinite, which is not, but if we have some, if we do have some kind of boundary, it's still, a very, very large dimensional system that we have, okay, which, in principle can contain a lot of qubits, okay, and this is true. So, if you, because the Shor's algorithm you saw, it can be done using, quantum phase estimation, and you actually need, quite a lot of, control qubits, but all these control qubits can in principle be replaced by a single continuous variable mode. Okay, so we can also have, we can also do quantum phase estimation using a continuous variable mode using what it's actually called a squeezed state. Anybody's heard of a squeezed state here? Okay, cool. Yeah, so this is something that is the bread and butter in quantum optics. Yeah, so you can actually use a squeezed state, but just a single mode, like a single state of a laser, right? As the only control mode, right? And the rest can be very noisy qubits. And you can perform things like Shor's algorithm, or you can find traces of large matrices and so on. Okay, so this is, and for those of you who may have heard the term, this is like a continuous version of DQC1, all right? Yeah, so factoring can be powered by a single clean Q mode, but of course, you say, well, why don't we then do it? Well, it's because the amount of squeezing you need is super large, okay? And actually getting very high squeezing is really similar to actually having very high energy input, okay? So the energy is too high, okay? That's required. But at least it gives you a sense, okay, of how Q modes are actually different from qubits. All right, so yeah, so in the 3 lectures, I'll talk about several methods that we have, but that's all related to schrodingerisation. And the philosophy behind all of this is what we call dimension lifting. Okay, so because typically in mathematics, when you're dealing, method of dealing with high dimensional systems, there are all the ways of reducing it to lower dimensional systems, so you can fit them on a classical device and work with them. Whether or not they're moment closure methods, or you have a lot of different types of methods. But however, we know that if we use a quantum simulator, then we don't worry about dimensionality so much, right? Okay, because quantum systems can deal with high dimensions. So how about when we take a high dimensional system and then increase the dimension by a little bit, right, to make them simpler, okay, in some way, according to our criterion, simpler, and then we simulate them on a quantum device. So that means we can deal with these simpler systems, right, and not also incur an extra recursive dimensionality, right? And this first method is schrodingerisation. So this is how we turn linear non-Schrodinger equations to become Schrodinger-like equations by adding a single dimension. Okay, so and later we'll have also methods for dimension lifting, where we change nonlinear problems into linear problems by increasing the dimension a little bit. Those of you who do machine learning, you know that with kernel methods. Okay, this is an example of dimension lifting. Okay, to make things simpler. Okay, but we will talk about other kinds of lifting. With uncertain PDs, there are ways of, if we have n uncertain problems with L uncertain variables, they can become deterministic again by doing this dimension lifting type of methods. And for no one who cares about non-autonomous systems, so we also have methods of turning linear non-autonomous systems to become linear autonomous systems, again by adding maximum of 2 dimensions. Okay, and this will get around certain problems with difficulties in simulating time-dependent Hamiltonian systems. Okay, and the message is that all of these these mathematical techniques of lifting the dimension, they're classically costly, so that's why people don't look at these in the classical world, but they can be potentially more efficient with quantum simulation, okay, because now we can put these methods onto quantum devices. All right, so this is the basic philosophy for the next 3 lectures, okay? So classically we kind of go from high dimensional to low dimensional, okay? But now with quantum computation, because we can try and resolve the curse on dimensionality, we can take low dimensional problems to lift them into slightly higher dimensional problems and then put them onto quantum devices. And it will make things a little bit more easy, okay? All right, now I will finally get to the topic, but before I go on, do we have any questions on anything right now, or anything you guys want to discuss, or no? Okay. Okay, so part 1 is about the basics of schrodingerisation, is how to turn linear non-Schrödinger's equations into Schrödinger-like equations. So what do we mean by non-Schrödinger equations? And we're going to look at linear ones, today. But we have 2 kinds. We have either a system of D, ODEs, right, or little d plus 1 are PDs. And I'm going to write everything in first derivative in time, okay, but we can promote high orders in time later, okay. So now, how do we turn these equations to Schrödinger's form? Now we have to think about 2 forms of Schrödinger's equation, okay, one in the ODE form and one in the PDE form. Okay, so Schrödinger's equation has the ODE form. Okay, and this is typically, the kind of ODEs that you normally see, I guess, in quantum computing when you're dealing with qubit systems, or in quantum chemistry, okay, a lot of the time. Where now your Hamiltonian that you deal with, it's a D by D Hermitian matrix. So again, here we're in the matrix language. But remember, this is now an ODE, okay, type language, okay, that's discrete variable. But we also have the PDE language, and this is Schrödinger's original equation, right, so instead of now the Hamiltonian being a finite dimensional matrix, now it's in terms of operators. So these are now infinite dimensional matrices and acting on continuous variable systems or Q-modes. And already you can see what the form of the Hamiltonian looks like, because if we look at the Laplacian, if you remember this rule about replacing derivatives, right, with IP hats. Okay, so now if you have second derivatives, right, then it's IP hat squared, okay, right? So then it's minus P hat squared, and then this is the same thing as having P hat squared, right? Remember, X gets promoted to X hat, right? And this should be very familiar as kind of a first quantization way of thinking about quantum mechanics, where you're promoting the momentum that you have in kinetic energy, classically, right, the momentum there into a momentum operator, P hat, and X, and then you have your usual potential energy, okay, side. Okay, so remember, the goal now is to turn, if you have classical system of d-dimensional ODEs, you want to turn it to the left-hand side here, okay? But if you begin with little d plus 1 dimensional PDs, then you want to turn them into equations that look like the right-hand side, okay? Where now the Hamiltonians are infinite dimensional operators, yeah? Okay, and I just want to say a word about classical versus quantum solutions. It's actually extremely important, which I won't talk too much about. And this is the following, that, classically, when we have, when we solve, PDs and ODs classically, we can read out the solutions, okay, very easily, okay? And this is because, partly copying comes for free, all right, as well. Okay, so we can read these out very easily, and we can know these, solutions for any time. But with quantum solutions, as soon as because quantum simulation, you're really saying you're using a quantum system, you're watching the quantum system evolve, and at the end you get a quantum state. Okay, if you don't measure, you still have a quantum state. Okay, so you're not reading out anything. Okay, and typically the solutions, they're what we call amplitude encoded, meaning the solutions that you want, it's encoded as the amplitude, right, corresponding to the quantum states. But it requires extra effort to actually read them out. So if we want to read out every single entry, then we're just going to lose. Okay, we might, benefit from, not having the cursor dimensionality in the simulation process, but certainly if you want everything at the end, you're just going to lose that. Okay, because unless what's called quantum tomography comes really cheaply, and strictly speaking, it's expensive, right? Because you have to measure so many times. But if it's easy, then we don't care. Okay, it can still be done, fairly quickly, so that's possible. But if you really just care about the number of times you want to measure something and how many copies that you want, then yeah, so we're going to lose. So instead, it's good to focus on a set of just observables that you care about, because this is kind of like a fair way of comparing them. Okay, so because maybe a lot of the time, for classical problems, we don't care about the whole solution set. Sure, the whole solution set makes pretty pictures, okay? But in terms of answering the questions that we want, maybe we don't, need the full solution set, but we only care about certain observables, okay? And in this case, so we can measure expectation values of the final states we have and then compare those. But what I'll focus mostly on is just the simulation process of getting to this step, okay? What are called amplitude encoded quantum states. All right, so this is a tiny summary of what we're going to do, okay? So to solve PDEs classically, okay, there are two ways classically. You can solve it digitally, and unless you use Monte Carlo, okay, which in itself has problems. But if you use more traditional, like finite difference methods and all these type of methods, then digital classical computers, we know that for PDEs you can have the cursor dimensionality. Okay, but with quantum, right, if it's possible to, in digital quantum, you can discretize a PDE and map them onto qubit type of dynamics. And here, if your problem satisfies, certain things like, the corresponding matrix is sparse and condition number is good and so on, then the quantum cost can be polynomial in dimension and logarithmic in n, okay, the number of discretizations that you have. So you're like, okay, this is an improvement, okay, upon classical. But you can also have, classical analog, right? And this is what I was saying, earlier. So these are the earlier type of computing machines, but they're really often for ODEs, okay, ordinary differential equations. So now, if you want to use these for PDEs, right, you still have to use many of them, because in order to solve a PDE with ODEs, it's really about discretizing your PDE in terms of its spatial dimensions, and to make them into an infinite system of ODEs, because a PDE is really an infinite number of ODEs. But because we can't, in parallel, have an infinite number, okay, solve an infinite number of ODEs, we have to discretize, okay, we have to truncate at some point, and then we're able to simulate them. Okay, so if you want to use classical analog methods, you need to use parallel computing, and you also need to discretize. Okay, so you do have to sacrifice some of that. But in the formulation in quantum analog, on the other hand, as we'll see later, we can exploit having entanglement, okay, in our system, so we can actually map the PDE directly onto a continuous quantum system without discretizing. Okay, and in this case, the quantum cost is linear in dimension, and no discretization is necessary. And if it's possible to actually find a real quantum system that satisfies with a Hamiltonian with the dynamics that we want, then it's basically one gate. Okay, so we'll give examples of that later. But this is what we're going to have a look at. Okay, and the benefits, okay, of analog quantum simulation: we don't need to discretize. Okay, and we can potentially utilize existing Hamiltonians without breaking them up into lots of gates. Okay, so using what people already have in the lab. It also mimics the history of classical computing. Okay, so it evolved from analog to digital classically, but we somehow haven't really passed through a lot of these steps for quantum right now. because digital has been so successful, people are like, let's just go straight to digital. If we have time at the end, we'll maybe also touch upon some foundational questions, okay, about emulation, okay, or how one physics system can simulate another. And here also the formulation, okay, in the continuous side is easier when learning for the first time. Okay, so of course, later if you want to solve PDEs with very complicated boundary conditions and so on, it's always good to go back to the original discrete language. But at least learning for the first time, I find it easier in this formulation. So I'll finally get to what it is, all right? But I do want to warm up with that a little bit because, like usually when students first learn about it, they think in this qubit language so much that, it can, be kind of a bit confusing, all right? So I do want to get that background. Okay, so now we do a warm-up heat equation example, right? So if we look at, a fairly general, okay, we're going to look at first derivative in time, okay, for now. This is a fairly general, linear form of PDE, okay? And if we look at the example, okay, we have Schrodinger's equation where the linear operator, has this minus I, okay, with a Laplacian with a V. And then we have a heat equation, okay, form. Where are they similar and where are they different? It's like basically the same equation almost, right? Except with an I. So now our question is, how do we get that I? Okay, because that's really the only question to ask, right? Because if you want to simulate a heat equation with, and some people, they say, okay, so I used to do high energy physics, okay, and people work a lot with work rotation and things like that. So they say, well, it's an I, obvious, right? T becomes IT, okay? There's nothing wrong with imagining time. We have, many dimensions anyway, so it's not a problem. Okay, so that's one way you make time, imaginary, okay? So T goes to IT. However, it won't reproduce the solution for you easily at any point T. So we really want a real-time way, okay, without, making abstract changes, okay? We want a real-time way of getting rid of this I, okay, or maybe gaining this extra I, okay, so that's the goal. And this is the trick, okay? Again, we use the dimension lifting idea, so we say, well, we have our usual spatial dimensions, okay, in X, and let's just work with one dimension, okay, for now, for simplicity, but it doesn't matter, okay, and we increase one dimension which we call psi, okay? And then we perform something that we call a warped phase transformation. Okay, so the extra dimension you can think about as a phase. And the warped part is, you multiply a factor, e to the power of minus psi at the beginning. And just a little story about how this name came about. So again, I used to do high energy physics where, it's not unusual to have extra dimensions. And I worked on a gravitational model called the random Sundrum model, where they will try to explain why gravity is so much weaker than the other forces. So the idea is that you have an extra spatial dimension that gravity leaks out into it, but is warped, right? So then we don't see it, okay? And this is why we have this exponentially decreasing factor e to the power of minus psi. And you're like, okay, well, what's the point of that? That's just like such an easy looking transformation. Well, we actually see that if we can ask the question, if U satisfies the heat equation, okay, so the box in green, then what equations does W satisfy? Okay, because if we're able to solve, okay, the equation for W, then we can actually recover, right, U fairly easily, okay, by either taking an integral between 0 and infinity or picking a particular side that is above 0. And then we end up with, so if we do, plug in the math, okay, then we notice that, the equation for W, it looks like this, okay? So this is called the heat equation in warped phase space. And if you look at this equation, you're like, oh, did we just make things more complicated, okay? But no, not really, because now we see that this is real, you can think about this kind of almost like a transport, okay? But now across the extra dimension psi. And it's actually, a transport where, our solution W, it moves from the right, okay, the right-hand side. So for you, it's this side, okay. So the right of psi to the left, okay. So which means we only need to input a boundary condition on the far right, and we can say that's, infinity. And we know the boundary condition because we multiply by u by the factor e to the power minus psi, and when it's really far and infinity goes to 0. Okay, so that's an appropriate boundary condition. And then it moves to the left. Okay, but we can actually extend the initial data into the negative region as well, because the solution does not impact the positive region, because the motion goes from right to the left. Okay, so now with the initial warped phase transformation, when psi is above 0, we multiply e to the power minus psi, but we can extend to the negative, okay, without consequence, okay, in this case, by symmetrizing this. Okay, so now it's a kind of tent, type of function. And if you look at this, you're like, okay, well, did we get any closer to what we wanted? Right? Because remember, the goal is to get an extra I. Okay, right? So how do we get an extra I out of this? Okay, so remember here what's really different is that here we have a derivative, right, with respect to psi. So how can we get an extra I when we're dealing with derivatives, right? And it gets back to our original what we saw originally with when we saw e to the power minus ixp. Okay, when we have Fourier transforms. Okay, so remember, if you have Fourier transforms, you multiply, okay, inside your integrand something e to the power of I, okay, xp, okay. If you take a derivative, right, of one of the either x or p, what happens? You get an extra I at the front, okay. So now this is the trick. We do a Fourier transform, and indeed, okay, we notice, so psi, remember, is the extra dimension, and eta is the conjugate mode to psi. So these are like the xp conjugate pairs. So now if we transform the equation with respect to w tilde, right, and we take a derivative with w, then we see, we just get an extra I at the front. Yay, okay. So this is the real-time way, okay, of thinking about this. But we notice that if we do take a derivative with respect to psi, we not only get an I, but we get an eta out at the front. But you're like, okay, well, this eta, how do we interpret this? I mean, there are different ways of interpreting this. You can think about, Schrodinger's equations for each Fourier mode, right, where, time gets dilated by a real factor, okay, eta. Or you can think about this like an infinite number of Schrodinger's equations, and you're like, oh, it's an infinite number, which is, we don't have them, so we have to truncate again. But no. This is the power of continuous variable, okay, systems, where we don't need to truncate anything, okay, at this point. We promote them to operators, okay. So here, the rule, x goes to x hat. Now, remember, eta, it's the, because it belongs to an extra dimension, you can think about it just like x or p, but now using a different mode. Okay, but what I mean by different mode is that in one dimension, you have one laser beam, and the second dimension is like a second laser beam. So it has their own independent, like xp. Okay, but I don't want to write x again, right, to prevent confusion. So we have eta now goes to eta hat, but eta hat is conjugate to psi hat. Okay, and they satisfy their own psi hat, eta hat is proportional to I identity. Okay, they have their own Heisenberg uncertainty. Okay, principle. And again, our trick with derivative ddx goes to ip hat. Okay, so now if we input all of that back into this equation, then we see actually this is a Schrodinger-like equation now with this modified Hamiltonian, and we deal with this infinite number, right, by adding in an extra quantum mode, Q mode, right, and we have a tensor product between the original kinetic energy plus potential energy part that we're familiar with in Schrodinger's equation, but now tensor product that with an eta hat, okay? And this is it's actually an entangling gate, right? So what the entangling gate means is that if you have these two modes, right, and then you perform an operation across these two modes, then you're going to get an entangled state at the beginning. If you didn't have one at the beginning, you're going to get an entangled state, okay, after you perform this operation. Okay, so now what we've done is that we've identified, right, a quantum Hamiltonian, right, where in a real-time way we can actually simulate, like, the solution of the heat equation if we embed the heat equation solution in the amplitude. And so if we're able to find a real physical, quantum mechanical physical system, right, on two modes that has this part of the Hamiltonian that we want, we can just directly use that, right, and simulate the heat equation. Yeah? Do we have any questions at this point? No? Okay. Yes?
Why are you identifying this new variable with x? The operators.
Why?
Yes.
Oh.
Can you repeat the question?
Oh, sorry. Yes, sorry. So the question is, why are we able to promote these regular variables into an operator? Oh, sorry. Okay, so the question was, why is it that we say eta hat can act like any quadrature, like for example, eta hat is equal to x hat? It's easier if maybe I can write on here, but maybe people can't see in the back. So I'll explain this way. Okay, so if we have, so here we're looking at a single mode, right, x hat and p hat. So for every mode, right, you can have your momentum and position pair, right? But now we're acting on two modes, right? So which means that now, so if we have two modes, we have like x1 and x2, okay? Yeah.
Just a different label.
Yeah, exactly. Okay. Is that clear to everybody? Yeah? Yeah. I just didn't want to write another x because, yeah. Good. Okay, but this is the crux of things, and we choose the heat equation to look at because it's somehow, the opposite of Schrodinger's equation, right? Right, because of this extra I, right? Because, I won't get to that point yet. Okay, but before I go on, I just want to say, well, we've simulated now this, W tilde state, but we haven't got back to our U state yet, okay? Because we have to perform an inverse Fourier transform, right? And then also somehow, do this integral, right? Or select, a psi that's above 0, okay? To recover our U mathematically. But what's actually happening, quantum mechanically? Well, remember what I said about in this continuous formalism doing Fourier transforms is super easy, right? Because you're just changing from one basis, like x into p and p into x, or in this case, eta to psi and psi back to eta. And here, so essentially, we don't even need to do, a Fourier transform like as an extra gate. We just change the basis of measurement at the end. Okay, so this W tilde to W is, this W tilde to W part is very easy to do. Okay, this step. And now, once we get W, what do we mean, when we do integral 0 to infinity or choose psi star above 0? Now, this is just a projective measurement, right, onto this extra mode that we've made. Okay, so we can think about this as an ancilla mode to the system. And if we're able to, now if we make this measurement, this projective measurement, and we only select the cases where psi is above 0, okay? And then once we can guarantee, okay, by post-selection this psi is above 0, then the rest of the states that we have, we guarantee, okay, that to be the U state. And the probability of success, like for that, it's proportional to the norm, okay, the final norm and the inverse norm, and the initial norm. We can get rid of this square as well, right, to make it linear, okay? So you have to do some amplitude amplification for that. But at least in the simplest formalism, okay, we don't care about the square so much. And you can see actually from this algorithm then has an inbuilt way to calculate the normalization constant. Because typically when people work with these PD type of problem, you say, well, then we need an extra quantum algorithm to compute the normalization constant, right? And actually a lot of the time that is what's very costly. But here we get it for free, because here when we're making an extra measurement on the ancilla, we just have to count the number of times, right? We get psi above 0, and we know that this is actually are equal to this normalization factor. So we kind of get that for free. Okay, and I'll give you guys a circuit later. Yes?
So how do you understand the fact that when you reverse the time, the differential equation is not anymore opposed, but now you already have the equation to determine the equation to resolve those?
Yeah.
How do you recover that?
So I will actually be speaking about the reversed heat equation later on, so in the ill-posed case. But here the question was, here we have a dissipative equation, okay, so diffusion, so meaning that you're losing information. Okay, that's another way of thinking about it. Like, So you start off with maybe a Gaussian here, and then it becomes like a fat Gaussian, you're losing information. So that if you go backwards, right, that's actually an ill-posed problem. But Schrodinger's equation, is unitary, so it can go back and forth, it's reversible, okay? So how we're able to, somehow why is this method able to somehow merge these two? And the way it's able to do this is really with the measurement step. Okay, so maybe this is a good time for me just to show this diagram. Maybe it's easier, okay, to see this. So here we have the initial state preparation, okay, U with an ancilla, and at the end, right, we have to measure the ancilla, right, that's post-selected. But once you do post-selection, so everything up to this point where we, do the Hamiltonian simulation, everything here is unitary, right? But the measurement is not. Okay, and the measurement, it needs to be post-selected when psi is above 0, and only then, right, we recover the state U of t. Okay, so yeah. But I will be speaking about how to do ill-posed problems as well, okay, later on. That's a good question. Okay, so now what about in general? Okay, so we looked at the most dissipative equation, okay, but most things are somehow in between, right? So if we look at, any linear homogeneous PDE, so it could be kth order, spatial derivatives, d spatial dimensions. I won't talk about high order time for now, okay, but I will get to that. And here we can use our rule, okay? Whenever we see, x, right, it goes to x hat. Whenever we see a derivative, right, it goes to IP hat. And here the subscripts here refers to the mode, right? Right. So when you have, x hat 1, this is x hat performed on the first mode, right? And mathematically, this is x1, which means the first dimension, okay, x. So now if you do this rule, right, we see that now we can change this PDE, right, really into an ODE-looking equation, right, except now this A, right, instead of being, a matrix, this is like an infinite dimensional matrix because it's a function of x hats and p hats. But now it's in an ODE-like kind of form, okay? And if we do this promotion, okay, x of I, so meaning the ith dimension, okay, x goes to x hat I, so this is x hat performed on the ith mode. And the derivative, if you have a kth derivative, then this is IP hat to the power of k. And if you do this, right, when we get our A, we notice that, any A operator can be separated very easily into its completely Hermitian part and its completely anti-Hermitian part. Okay, so A is equal to A1 minus IA2, where A1 is completely Hermitian, right, and A2 is completely Hermitian. Okay, so obviously then IA2 is completely anti-Hermitian. And it's done very easily because it's A plus A dagger, okay, so that's the Hermitian conjugate, and the A minus A dagger, okay, adjoint. So if we notice that if we just look at the Hermitian part, okay, that's A1, if we only had A1, that's just Schrodinger's equation, okay? But if A1 is 0, okay, we only have A2, then that was just like the heat equation example we had before, okay? So, I just want to note here, the original system is stable, okay, when A2, okay, is above 0. We will talk about cases when it's not, like later, but at least for the simplest formulation, when it is. And then our Hamiltonian, right, so we do the same thing, we do the warped phase transformation, okay, it's kind of like the same deal. But now the Hamiltonian, you see, has this form, okay? So it's A2 tensor product eta hat plus A1 tensor product identity. And this should be maybe, very expected, right? Because if we look at A2, like remember that's kind of the heat equation part, okay? That's a completely dissipative part. And then we already saw in the heat equation example, we just take the original part of the Hamiltonian and tensor product that with eta hat, okay? That's what we did. But remember, A1 is just the completely Schrodinger's part anyway, right? So we don't need to do anything with the second mode. So that's why it's the identity. Okay, so now if you take any operator A, right, then this is the general Hamiltonian, okay, that you need to simulate. And the state recovery process is the same. Okay, so you start off with your initial condition plus your ancilla state, and then you evolve this system together, right, using this Hamiltonian on one extra mode, right? And then you measure your ancilla, right? So that your psi is above 0, okay? And the rest of your state you're guaranteed to be the state that you want. Okay, so this is the kind of schematic diagram. And here we're looking at an autonomous system. But it works also for non-autonomous. It's just that it will be more difficult for me to write out this guy, the unitary, right, for non-autonomous systems. So the initialization is that you want to initialize your, whatever initial condition, okay, that you have for your PDE. But the ancillary state, this is fixed, actually, for the schrodingerisation formalism, in this, simplest form. And this initial state, you're like, oh, what kind of state is that? Well, it actually turns out to be very, very, very close, right, to a state that is the coherent state. Actually, the state that directly comes out of your laser. So this is something that is, quite doable on a lot of quantum devices. So you can put this in, and actually the final result will not differ like so much. Okay. So we have some simulations on this. Yeah. And then, so if you want to, so in other words, if you want to simulate a capital D dimensional PDE, linear PDE, okay, of the forms that we looked at, then we just need D plus 1 Q modes. And if you remember what I said maybe at the second or third slide, we have like millions of Q modes available. Yeah. So we're not really out of Q modes, okay, right now. Yeah, and this is the probability, and here then we do a post-selection. Okay, so remember doing this integral just means we just measure, okay, in psi. And by measuring psi, we've actually automatically done the Fourier transform. Okay, so because we really changed this eta hat, like in here, instead of measuring eta, if we measure in psi, we've already done this inverse Fourier transform. Okay, and it kind of comes for free. We don't need this, all these extra gates. Yeah. And the probability of success, I said, is related to the normalization. Yeah. So, and I want to say something about the initial state preparation. So in principle, okay, the initial state can be in principle prepared for any boundary condition in X and T is equal to 0, as long as the U at the beginning is like smooth enough. Okay. This is, a schematic to remember the procedure on how to do this. Okay, I think it's very simple. So you start off with your, linear PDE, and then all you do, whenever you see x, it goes to x hat, right? Whenever you see derivative, it goes to IP hat. Okay, and then you're going to get a form like this, where your A now is a function of x hats and p hats. And now you find out the completely Hermitian and completely anti-Hermitian parts of your A, right? And this is A plus A dagger or A minus A dagger, okay, very easy. And then your Hamiltonian is just A2 tensor product eta hat plus A1 tensor product identity. Okay, so we don't need to do any funny operations. So, with things like block encoding and so on that you've seen all week, you have to do like squares and square roots of stuff, right? If you remember, things like that. Which is very good, for general problems. But here for PDEs, actually we see that, this is, the criterion of simplicity, right? And here what's also good is that if you go to your experimental friend, you say, okay, what kind of Hamiltonian do you have in the lab, right? Then you just match what you have, and you can go backward, okay, very easily, right? Because everything here is kind of linear, right? We don't need to do square roots or squares or anything. So. Here, if your friend has Hamiltonian of this form, you say, okay, what kind of A1 and A2, okay, you have. And once you have your A1 and A2, you can find your A, right, very easily. Okay, it's just A1 minus I A2. And once you find your A, you go backwards. Whenever you have X hat, you go to X. Whenever you have P hat, you go to the derivative, right? So, and this is kind of the procedure that we start off with that, could kind of go back and forth. And of course, everything that we do here, it can be discretized and just, the usual way that you do, numerical methods in PDEs, you can do this as well and still keep in a continuous time. But I want to introduce it in this way because I think it's just easier to remember this way. And you can always make things into matrices later. Yes?
So the last time after this, you just do a measurement of the extra mode.
Yeah, so the question was to clarify what we do in the last step, right? Like how do we deal with the inverse Fourier transform? Because remember, we derived the Schrodinger-like equation W tilde, right? But to recover like U, it's doing an integral over W, which is the inverse Fourier transform. So where did the Fourier transform go? And remember, it's the Fourier transform only in the ancilla mode, okay? Not in the X modes, okay? On the other ones. And here, in order to do the Fourier transform, instead of putting a gate here directly, right, you just change the basis of measurement, right? And it's the same thing, right? So you know, you can either, if you have a system and you want to do a Fourier transform and then measure in X, that's really the same thing as, you know, doing what you have, but instead of doing any Fourier transform, you measure in P. Okay, so these things are equivalent. Yeah.
So you don't do any post selection based on the result of that measurement, you do a renormalization of the
So the question is, after post-selection, do we have do anything else? The answer is no. So we simply measure, okay, in psi and ask, is it above 0 or not? If it's above 0, then the state that we have here is automatically the state that we want. Yeah, and the probability to which that occurs is actually related to the normalization. Yeah. But it is definite. Like, you always know if you succeed or not, because it depends on the measurement result of your ancilla. Yes?
Is there an intuitive explanation why if you have a signal that decays at long times, then the probability of getting the result is going to decay?
Well, yeah, because you're further and further away from Schrödinger's equation. Right, because here, if you think this is like completely, if this is 1, for example, like you would have for Schrödinger's equation, then you shouldn't, you know, you should succeed all the time, yeah? Because it's like you didn't need this extra mode to begin with.
So is it to say that if I have a more dissipative system?
Yes, and I think it's also related to the fact that because it's dissipative, like you would have more of the effect of measurement. Right, because somehow by doing measurement, it's related to Marzier's question before. Like by doing the measurement, this is like kind of the quantum way of saying before we had conservative system, and now we've lost the information. Right, so the more dissipative you have, the more information you've lost, and therefore the lower probability you should have of recovering, right, the original equation. Yeah, I mean maybe there's a better mathematical formulation, but this is the.
So
yes.
I haven't paid attention. What eta means next slide.
Oh, so the question was what eta means in this slide.
Next slide.
Oh, in the next slide.
This one.
What?
Yes, this one.
What eta means?
Definition of the Hamiltonian. Eta.
Oh, what this? So the question is what this eta means here? Oh, from a physics point of view. Okay, so the question is what this eta means from a physical point of view, and this is for me, like eta is just a notation for me. Like you should think about this as momentum in the second mode, but I just didn't want to write P2, right? But it's the same thing.
But
so,
did you
yeah.
actually choose it? I mean, it's arbitrarily chosen when you do transformation, or you have to solve it?
How do you choose it?
Choose it?
I mean, is it like an arbitrary choice, the eta operator, or is you just have to solve it? It comes with the solution.
You have no expression on eta.
When
Sorry,
you do
I'm not understanding the question.
When you get back to the definition, when you add the two modes in the previous one of the previous, I think
this one?
Merci. Thank you. Yes, here. I think it was maybe in the previous one.
This one?
Yes,
Or
here.
this one?
Yeah, I think it's here or even the one before.
Oh.
So the eta coefficient or the eta value here.
Okay, nice.
So you get to basically. It looks like a modifier, but I don't understand how do you choose the eta. It looks like some sort of.
So let me try and rephrase it to see first if I understand it, because I don't think I do exactly. So maybe psi and eta is a confusing thing. Okay, so let's just think about x and p, right, in another dimension. Okay, so and here this is just a Fourier transform. So this is not like a choice. Like if you define what psi is, right, you know its conjugate.
Okay. Yes.
Okay, so that part is already defined for you, and then to initialize, maybe what you mean by choosing is, remember we initialize our state in terms of e to the power of minus psi. Okay, so in the particular basis of psi, if you're able to prepare this state, this kind of tells you what psi is, and then eta is the conjugate mode to that psi. Yeah.
I got it.
Is that okay? Thank you. Yeah, please, like anything that's unclear, please just shout out. So then, yeah, because sometimes I just run over things and then I forget. Maybe I didn't make something clear. Because this is not the usual language, actually, that people present algorithms in. So that's why, there could be a lot of things that are very confusing. So please don't be afraid to ask. Yeah. Yes. Yes.
So this, okay,
No, the question boils in how to implement such a Hamiltonian. But is it? While I can see maybe through some effect, you could have such kind of Hamiltonian in an effective manner, but is it possible to have such a Hamiltonian by quantization of a physical system? Let's say starting from a Lagrangian and then trying to write a Hamiltonian, because you don't have any quadratic term in P, for example, any kinetic energy or something. How would you? This effective Hamiltonian in eta that you find. So, for example, if eta is the momentum, or psi.
So let me try and rephrase because I don't think I fully understood it. So you're asking where did the p hat squared go?
No. Well, p hat squares might be. You have added this new mode, right? Which is this new Q mode. You have eta in this Hamiltonian. You don't have eta squared, for example.
Oh, okay. So the question was. If I understood you, please keep the mic because maybe I haven't understood you. So the question is that this is not very general, right? So this is like, okay, well, to the extra mode we only have to add eta hat, but we won't have things like eta squared and all of that. So what happens to all those modes? Well, so this is a good question. So if we want the corresponding kind of kinetic part, right, to this, then we do need to add in like an eta hat, but actually. In a lot of physics situations, they perform what are called like rotating wave approximations. Like for those of you who might have heard the term, what this means is that because in physics, you're always going to have these kinetic terms, right? You always have kinetic energy, and these are independent kinetic terms, meaning that you only have individual harmonic oscillator, the kinetic part like of those, and they don't couple with others. Right, so there are always ways of changing your basis in a way that you rotate them away. So you only look at that interesting part of the Hamiltonian. Okay, so with respect to finding a real physical system, this is the interesting part of the Hamiltonian that we have a look at. But in fact, like usually for real physical systems, you might even have other terms, right, which technically belong to the interesting part, but still are not of this form. And then you have to use quantum control type of methods so that if you have coefficients in front of them and make them really, really, really small, like you want to damp them. Okay, so this is the where the area of quantum control comes in, right? So people study like the real physics of these systems. How do you tune the parameters in such a way that the interesting part actually matches, okay, what we want? Yeah, so that's a really good question and a really important one.
Okay, maybe we have time for one more question and then we'll have the coffee break. No? Okay, so I suggest we
okay, sorry, I didn't realize it was already an hour and a half because, okay. I'm not even like halfway
really
through.
sorry.
Okay. Oh, no, sorry, it's completely my fault. I didn't realize,
So,
yeah.
Anyway, I suggest we stop here and thank again.